no water, life stops. There is but silence, where once were heard the voices and the steps of men, of women, and of children. Man's history, his very existence, has ever been determined by his supply of water. Through the years, he quenched his thirst in nature's brooks and springs, or dug deep wells to draw the water from the earth below, or pumped it out. For his supply of water, each man depended on himself. But man has built great cities. They must have water. His buildings now reach for the sky. His numbers now are legion, and so man can no more rely on nature unaided. He now must have great water systems. Every modern system must have three basic things. First, a source of water, sufficient at all times and through all seasons. Second, a method of purifying the water to protect the city's health. And third, a means of pumping the water through the mains in a never-failing stream to the people of the city. The powerful surging waters of the Missouri River, the Big Muddy, are the source of one city's system. Here, mingled in the turbulent flow, are waters from the mountains of Wyoming and Montana, from the plains of the Dakotas, of Nebraska, and of Iowa, a mighty flow of water which is tapped for Kansas City. The water is drawn in at the intake building on the deep current side of the river 4 miles above the city. This building rises from the bed of the river, so that no matter how low the surface level, the water supply will never fail. The water must pass through the intake bars, which keep out driftwood and other large debris. The water must pass through a series of revolving screens, then is drawn up and out. The screens behind the bars are fine enough to hold back the smaller cargo of the river. Powerful jets of water at intervals are directed against the screens to keep them clean. Just north of the intake building is the low-lift pumping station, which draws the water from the river intake. Within this building are the first of a series of power machines. 5 huge electric motors drive the centrifugal pumps that draw billions of gallons a year to meet the needs of the Kansas City area. These mammoth pumps have a total capacity of 160 million gallons every day. Constant check and measurement of the flow requires a vast array of precision instruments and recording equipment. At the rate of over 27 billion gallons every year, the water is on its way to the first stage of transformation from muddy water to clear water. From the low-lift pumping station, near the river's edge, the water is pumped underground to the group of 4 clarifiers. These primary clarifiers are simply huge settling basins through which the water is moved very slowly allowing the greater part of the mud and other foreign matter to settle. Each of the 4 monster basins holds 4 million gallons. The huge capacity is easily seen when the basin is empty. Within the settling basin, the water loses most of its heavier mud and silt. The science of chemistry plays a vital part in the modern water system, and so at every stage, samples are brought into the laboratory. This is water as it comes from the river. After passing through the settling basins or primary clarifiers, the water is noticeably clearer. And so, having rid itself of part of its burden, the water flows out of the settling basins on its way to a chemical treatment, the first of several which originate in the chemical building. From the settling basins, the water enters mains underground. Here, the water receives its first treatment of chlorine from the chemical building. This initial chlorination destroys most of the bacteria present in the river water. While a full carload of chlorine is required each month, it actually takes only 15 pounds to sterilize 1 million gallons of water. The quantity of chlorine to be added is carefully controlled. From the chlorination point, the water moves on to the mixing tanks. In these great basins, located just east of the chemical building, the water receives the bulk of the chemical treatment it must undergo to soften, clarify, and sterilize it. The other elements necessary to the treatment of water are brought directly to the chemical building to be carefully checked and weighed to meet the requirements of modern scientific water purification. By a series of conveyors, the contents of the cars are moved to storage bins. From the bins, the chemicals are automatically released as needed to electric weighing machines or dispensers. These machines are adjusted to deliver the exact quantities of chemicals required. Chemists are checking constantly to make sure that the quantities released are those specified by the main laboratory. Every step in the purification of water must be scientifically controlled. Chemicals are fed by the dispensers into tanks to be mixed with water for ease in handling. The lime helps to soften the water. Ferric and aluminum sulfate will serve to clarify it. And sodium carbonate, or soda ash, is an additional softening agent. The solutions move into troughs leading out of the chemical building. The master flow meter shows the volume of water to be treated in the mixing basins. In the center of each basin is the mixing flume, where the chemical solutions are added to the water as it flows in from the clarifiers. Now, with the chemicals thoroughly mixed, the water moves out of the mixing basins. Flowing underground, it enters the primary flocculator, or first chemical reaction basins. These basins are equipped with flocculators. or mixing paddles, shown here in a working model. The purpose of the paddles are to gently agitate the water. Laden with chemicals, the water enters these primary reaction basins. Now the chemicals form sticky, gelatin-like particles known as flock. The chemicals have begun to do their job. If the process were studied under a microscope, it might look like this. Under the gentle agitation of the water caused by the paddles, the flock moves about, attracts, and absorbs the mud, silt, and bacteria. In so doing, the flock grows in weight and volume. This is the water as it enters the primary reaction basins, and as it looks after the flock has absorbed the foreign matter. The chemical reaction basins are full at all times under normal operation. When the basins are drained periodically for inspection, the size and arrangement of the equipment can be seen. Now the murky waters of the reaction basin are ready to move on into the larger basin, the secondary clarifier. The concrete wall separating the two has openings beneath the surface. The water, heavy with flock, moves through the openings in this wall into the clarifiers or secondary settling basins. The contrast in color between the water in the reaction basin and in the clarifier gives dramatic evidence of the change taking place. The comparatively quiet water of the clarifier or settling basin allows the billions of tiny pieces of flock to sink to the bottom, carrying with them most of the remaining impurities in the water. This settling process goes on every hour of every day. If it were not for the mechanical equipment, this tedious operation would have to be done often in order to remove the tons of sediment. It requires approximately 5 hours to drain the basin, another 5 to refill it. But in the center of each basin is a giant bridge-like structure called a sludge rake. It revolves on a pivot slowly so as not to agitate the water. It scrapes the sediment deposits from the bottom into a center drain, thus keeping the basins clean and free of sludge. This is the water heavy with flock as it leaves the primary reaction basins. And this is the water after the settling or clarifying process. From the secondary clarifier, the water moves on for further treatment. The water passes to an underground compartment for carbonation. From the chemical building, carbon dioxide is piped to the water. Another step in the water softening process. Here again, careful scientific control plays its part. The amount of the carbonation must be regulated with precision. As the water pours into the compartment, carbon dioxide bubbles up through it. The release of minerals from solution by carbonation gives the water a rather cloudy appearance. After carbonation, the water moves on for additional chemical treatments. Additional chemicals are applied at this point to further clarify the water. Activated carbon is added for taste and odor control. From From here, the water flows into the secondary reaction basins. Mixing paddles in the secondary reaction basins again keep the water moving, allowing the clarifying and softening process to go on. And to permit the settling of sediment, the water moves into the final clarifier basins. Even though the water at this stage is suitable for human consumption, modern purification methods demand still further treatment. The sample shows evidence of that fact. As a final step in the softening process, more carbon dioxide is added. With final carbonation, the water enters the filter building, the last stop through the purification system. It has taken 24 hours to bring the water from the Missouri River to the filter building. Within the building are 24 filter tanks, where the minute foreign particles remaining are filtered out. Here, as in all other purification steps, batteries of meters and recording instruments allow a constant check on operations. About every 3 days, equipment is set in motion to drain each filter tank for cleaning. Water passes down through the layers of sand and gravel to outlet pipes. Draining of the tanks is necessary when the filter beds become clogged. First, the crust on the top of the filter beds is broken up. Clean water is then forced up through the strainer system. The sand is lifted and thoroughly agitated. The foreign matter is carried away by the wash water. This filter tank can now be refilled and put back into service. One final purification treatment remains, the last application of chlorine, providing an extra margin of safety. Thus the transformation from the raw river water, muddy and germ-laden, to the clear, healthful water we drink. But laboratory control has not ended. Each week, samples of water are taken from zones throughout the city, submitted to bacteriological tests, checked for harmful impurities. Every device, every skill in modern chemistry is enlisted to produce and maintain the purity of your water. Next to the filter building stands the secondary pumping station. Housed in this building are 4 great electric motor-driven pumps, delivering over 27 billion gallons of water per year. The pumping equipment at this station guarantees an ample supply of water for the Kansas City area today and gives assurance that future demands as well can be met as the city grows. On the meters and automatic recorders is written the story of an unfailing public service. And so, from the purification plant, water is sped on its way to you. Through pipes dipping 300 feet below the Missouri River to pumping stations in the East Bottoms and at Turkey Creek. Located in the East Bottoms Industrial District, this station draws upon an underground reservoir with an 18 million gallon capacity. Its 3 mighty centrifugal pumps, electrically powered, deliver more than 7 billion gallons of water per year. The Turkey Creek Pumping Station, located in the West Bottoms Industrial Area, depends upon steam for its power. Its great boilers consume 70 tons of coal each day. Six units pump a total of more than 17 billion gallons of water a year. Under the impetus of the lift stations, the water, under controlled pressure, surges into the city's mains. Thus, to Midwesterners, hundreds of thousands strong, goes the unceasing flow of water, moving through the vast network of pipes and mains that crisscross the city beneath the surface of the streets, reaching every point where people choose to live and work. Extending into outlying areas, given new speed by booster pumps along its way. Stretching ever farther from its source to serve additional thousands as the city grows and expands its boundaries. Final safeguard, sterilization of the new main as it prepares to deliver its precious commodity. Testing to guarantee its unqualified purity. This, then, is the inside story of the everyday magic that taps the muddy waters of the Big Missouri. Treats it by the processes of modern chemistry, assembled for the job that must be done. Delivers it by the power of machines, harnessed for the task that must not fail. To give water for industry, water for the engines and machines that do our daily work, water to beautify our homes, water for pleasure and recreation, water for the means to safeguard our health, water for our homes ready to flow at any hour on any day, and water for the lines that every year save lives. This is the life stream of our city.